Right, welcome back to Maths Linear Algebra Tutorial 2. Today is the 3rd of September 2020. So today we'll do about 5 questions and then if I see that the recordings is okay, I'll post it up. So let's examine the first question. We are given a matrix A that is not square. So we have a m by n matrix. And we have a matrix B that is also not square. So this is a n by p matrix. And basically, as you know, that for a matrix to multiply, then this size, this guy's column must match this guy's row. And since it matches, then fine. We are left with a matrix C that is m by p. And then the question begins. The question says that we know that B column or B's are linearly dependent. Basically, he's saying that these rows, these columns are dependent. And what does dependent means? Well, let's have a very simple example. Maybe 1, 1, 1, 2, 2, 2, and then we have a 3 by 2 matrix, and then of course the second column of B is 2 times the first column, so they are dependent. And then here it says that fine, given B are dependent, what about the columns of AB? Or we call it C now, of course. So are the columns of C, this column also dependent? Right, so let's see what dependence means for us. So in this example, we have a 3 by 2 matrix of B. And if I multiply by 2 for the first column and minus 1, what do we get? We get 0 because it's 1 by 2 by 2 by 1. So we get 2 minus 2. And then for every element is the same. So this is quite surprising. I mean, basically we are saying B multiply, let's call this X. And let's call this maybe small b, we like small b. And then a matrix multiplying by a non-zero X give you the 0 vector. And we call this non-trivial because X is not 0, but yet the output of Bx is 0. And this only happens because B has dependent column. Now, so the problem, of course, is what about C? All right, so let's try on the right-hand side now. Basically, we're interested in saying, is Cx, so this is equals to 0, even if X is not equals to 0. If this is true, then if this is true, if true, then C has dependent column. So what is C again? C, well, let's erase this C and we put our AB here. So remember, C is equals to AB. But we know from the fact that because B has dependent column, we can find a X that is, what do you call that? We can find a X that is non-zero and yet the output is 0. Because, so A multiplied by Bx, because this Bx is 0, the 0 vector, the output is surely 0. So because of this fact, we know that this is true even though x is not equals to 0. And therefore, AB has dependent column. Okay, so this is the argument. All right. Now, because the matrix is not square, otherwise it would have been easier. Now you are learning determinant now. Now, when matrix is square, for example, A is square and B is square and C is equals to AB, then the determinant of C is equals to determinant of A multiplied by determinant of B. If the determinant of a matrix is equals to 0, then the matrix X is not invertible. Else, it is invertible. And when it is invertible, then when a matrix is said to be invertible, so that's the first line here, the matrix A is invertible, then all these things is true. So in fact, the question was whether this is true. Here, AX equals to 0 can only be true when X is the trivial solution, means X is also equals to 0. All right. So, but this is only for square matrix, so you have to be very careful in our question. Both A and B's are not square matrix, so we cannot apply this determinant reasoning. Okay. All right. Any questions, guys? No. Let's try the second question. Now here, the question is a little bit easier in the sense that now A and B are square. B is invertible. So he's telling you B minus 1 exists. AB is invertible. He's telling you AB minus 1 exists. Actually, please remember that when he tells you that B minus 1 exists, he also implies B exists. Here it also implies AB exists. Now, then the problem is show that A minus 1 exists. Because some matrices are not invertible. So I can give you a matrix, for example, A equals to 1, 1, 2, 2. And for sure, it's square. But you can check the determinant. It will be equals to 0. And therefore, the matrix is not invertible. Now, all right, how do we proceed? Let's try to remember, we're trying to find A minus 1 again, the inverse of A. Let's start with let C equals to AB. We post multiply the above by what we are given, which is B minus 1. Why do we want to post multiply the above by B minus 1? You realize that when we do that, we have C and B minus 1 equals to AB times B minus 1. Now remember something about matrix multiplication. ABC is equals to AB times C is equals to A times BC is equals to AB times C. So it doesn't matter which order you do. Yeah, whether you want to do BC first, you want to do AB first, whatever. But the matrix cannot be AB is not equals to BA. Yeah, so it is not commutative. It is associative. All right. Now, so what am I going to do? Basically, I'm going to get rid of the brackets A, B, B minus 1. Because by associative, brackets does not matter. And we can introduce the brackets any way we like. So we introduce it this way. And remember that when a matrix B multiplied by its inverse on the right, it will be identity. When we multiply an inverse by his left, it's also the identity. All right, so we just introduced B minus 1 on the right-hand side. We got rid of A. And if we are really pedantic, we can put I. I is the identity matrix of the correct size. And we put a little n there to say that this guy is the identity matrix of dimension n by n. Then, of course, we get rid of the I because I behaves like the number 1. So we ignore. Remember, I is like this. 1, 1, 1, 4, I equals to 3. Okay, so it's just a diagonal values of 1. That's it. If I is 4, then it's diagonal with 4 entries of 1s. So then the question is, hey, we're left with CB minus 1. Now, what was given to us again? B is invertible. So here is invertible. What about C? What is C? C is equals to AB. And then we have already been told that AB is invertible. So what do we have? A is the product of two invertible matrix. And then later on, there's some rule that says the product of two invertible matrix is, or the result is an invertible matrix. We are going to prove this, of course. And then when this is proven, then we say that, yes, A is invertible. Or we can say A minus 1 exists. All right, so now we are going to go to the next page to prove this. The product of two invertible matrix is invertible. Any questions so far? All right. Okay, let's start with let have two matrices square A and B that are both invertible. So implying A minus 1 exists, B minus 1 exists. What about their product? Is it invertible? So AB is their product. And if the inverse exists, X, okay? If the inverse exists, let's call him X. So does X exist? If it does, then AB is invertible, right? By the definition of invertibility. Okay, so the trick is very interesting. Basically say let X is equals to, and guess what X is going to be? It's going to be B minus 1, A minus 1. Now, why can we do that? It's because we are given that A minus 1 exists, B minus 1 exists. Then we form their product, and we can form their product because they are both square, so that's not a problem. And now, of course, what we want to test is this true? If this is true, then AB is invertible. All right, so what do? We plug in AB, B minus 1, A minus 1. Then we want to check. We open up the bracket. We'll close the bracket. And we see that B times B minus 1 is I. We get rid of the I because I does nothing when we multiply a matrix with it. Again, A times A minus Y is I. Okay. So therefore, X is equals to B minus 1, A minus 1 is the inverse of, and we've shown that, yes, when each of the matrix is invertible, their product is also invertible. Therefore, this is shown. Okay, so yeah, are you all right with question 2? Okay, if that is, then we go on to question 3. But you must remember this result, the question 2. Yeah, the product of two invertible matrix is invertible. Now, in question 3, let's read the questions again. A, B, X are n by n, so they are square. Remember that only square matrices are invertible. So fortunately, he says A is invertible, X is invertible. So A is here, X is here. A minus IX is invertible. So interestingly, he never tell you that B is invertible. Because later on, he's going to ask that if you're going to use B minus 1, then you must explain why it is invertible. All right. Now, suppose this is the condition given us. Solve X. So this, we start with A minus AX minus 1 equals to X minus 1 B. Phi X. So the first trick is this. He tells you that A minus AX bracket minus 1X exists. Therefore, he's also saying that A minus AX exists. Okay, so he's just saying the inverse exists. All right, chat. We'll need to prove that result for every question that required. Will we need to prove that results? Depends on the question, I guess. So like here, he's going to tell you that everything you must prove. Okay, so anyway, for the tutorial, I'll try to prove everything that we need to. And then it depends on the question. All right. So here, he tells you A minus AX bracket minus 1 exists, implying A minus AX exists. So that's all right. So what do we do now? So we are going to trick. We're going to say take the inverse on both sides. So if you take the inverse on the left side, you must take the inverse on the right side. So the first trick is this. If you have A and you take his inverse, you get minus 1. You take the inverse again, and then you actually get A again. So remember, it's just, so maybe I won't prove this to you. I'll just think of it as a reciprocal of a number. So you take number 3, and then you take its inverse, and you take its inverse again. So that's the basic idea. All right, but so in this sense, it behaves like numbers. Huh? All right, so what happened? a minus ax minus 1 minus 1. All right, so that's why I'm playing this trick. So basically, on the left-hand side, the inverse of an inverse is the same guy, a minus x. Over the right-hand side, inverse. Now, the other trick that you need to learn is, if I have a matrix A and B, and I take its inverse, then this guy is B minus 1, A minus 1. So here, we didn't prove, we just, let's say we are going to use this result. This is very similar to AB transpose, B transpose, A transpose. All right, so I'm just going to use the results. B minus 1, X minus 1, minus 1, B minus 1, X. All right. Now, of course, so we are not sure. Here we have a slight problem. And we have a slight problem because does this exist? And we look up in the question and says no information was given to B. All right, so what do we do? Well, let me see. Did I make a mistake? I've always made a mistake here. Let me check. A plus. Okay. Sorry. Let's wait a while. Then we progress, and now we get A, and we want to move minus AX to the other side. So we have AX plus B minus 1X. And then we collapse A plus B minus 1X is equals to A. And then at this juncture, we want to solve for X. So basically, we wanted to move this guy to the left-hand side. And this guy can be moved to the left-hand side if A plus B minus 1 exists. So let's play along first and assume that it exists. So we basically pre-multiply this first, and then later we'll prove that A plus B minus 1 exists. Okay, so it basically means A plus B minus 1 times A on the left-hand side, A plus B minus 1 on the left-hand side of the equation, A plus B minus 1 X. And this is, of course, the result we are trying to hope, because we can now cancel, and then we are getting X equals to A plus B minus 1 A. So we solve. But remember that we still have this question. Does this exist? So what do we do? Let's check. Let me see. Yes, here's it. We start from here. We are going to post multiply this equation by A minus 1. this equation here, we'll get a minus 1 on the left. On the right, we'll get a plus b minus 1 x times a minus 1. Okay, so I'm using a wrong equation. Let me draw this correct equation for you. I'm using this equation here. I am post multiplying a minus 1. So a times a minus 1 on the left hand side. The original guy, a plus b minus 1 times x on a minus 1. Now, remember this, what is given to us? X is invertible. What else is given to us? A is invertible. And therefore, this guy, yeah, is invertible. And not only that, on the left-hand side, you are given I. So implying this guy is invertible. So this proof is actually very long. Yeah. So this is the whole page you can see. And the tricky part is, of course, all the small parts that we are going to use that the matrix is invertible. Any other questions? I'm going to, yeah, so you can, going to save this recording and I'll put it up and you can go through it slowly. Okay. Okay, chat. What about the proof for B? I was worried someone will ask that. Okay, so I'm going to, so the gentleman or Gabriel asks, yeah, what about B, right? And did we use B? Yes, does this exist? Okay, so let's try. Let me check. Okay, I'm going to try to prove for B here. We start with this. We start with the equation A minus AX minus 1 equals to X minus 1B. Correct? So this was the equation that we begin with. Now, what about X? X is invertible. X is invertible. So we pre-multiply by X. Pre-multiply by X on both sides. What we want to do is X, A minus AX minus 1, X minus 1, B. This guy is the identity, so we can strike him off. So B is equals to, X is an invertible matrix. This guy is an invertible matrix. The product of two invertible matrices implying B is an invertible matrix. So did I answer your question, Graber? Okay. Yes, thank you. Why they ask to solve for X just need to express in terms of A and B. When they ask to solve for X, just need to express in terms of, yes, correct, Tai'an. They are asking you to basically find this equation. X equals to something. But to reach there, you've realized that we have to do a lot of inversion of matrices. So this whole exercise is an exercise for you to understand which matrices can be inverted and which matrices cannot be inverted, and what are the rules that we have applied, which are plenty. Oh, actually, maybe we have only applied that product of matrices, product of invertible matrix is invertible, right? So, which is this rule here, and which is the rule that I have just said, or which is the last what do you call that? It's not a theorem. It's just some rule that we have proven before. Okay, so I think we've done number 3. Okay. Chat. Is there a reason? Yeah. Oh, they're trying to trick us. Yeah, I was wondering that too. So I asked Dr. Tipu, and I think that maybe it's a typo. And if they are giving us the, you know, that if they've given us this matrix A minus AX, I think it's a typo because this matrix is useless, or this invertible information is useless. Okay, so I didn't have to use this. So maybe it's a red herring. Okay. So you guys have no problem doing this question, or am I doing it very lengthy as compared to you guys? I guess I'm just making sure that every steps are there. All right. Okay. Thanks for participating. Actually, it's very strange to talk to and teach in Zoom. Okay, chat. Can't even start. Don't worry about it. It's not easy. It's not easy. Okay. Yeah. So these exercises, even I find myself very challenged. Yeah. So it's quite difficult. All right. Okay, let's start. AX equals to 0 homogeneous system. The word homogeneous means this. My right-hand side of the equation is the 0 vector. So when you say that a system, the homogeneous system, it means that the right-hand side is the 0 vector. It has n equations, means the number of rows equals to n, and n unknowns, the number of columns equals to n. Where? He's talking about A, the matrix A. So A is a square matrix of n by n, where these are the equations 1 to n, and the columns 1, 2 up to n are the variables. Where is x? X is here. Let's call him x1, x2, and then we need xn because this guy is the x vector. So we have a n by n matrix multiplied by n by 1 column vector. The output B is equals to, so you must see that we must always check that the matrix agree, which it does. This is n columns, this is n row, they agree. Therefore, now we have a n by 1, which is this guy, and this guy, column vector. Okay. Now, so what are the other information he gave us? The second information he gave us is AX equals to 0. So he fixed the output. Output must be 0. And then he said trivial solution. What's he trying to tell us? He says X solution. The solution of the equation is X. So this guy must be the trivial solution, which is the 0 vector as well. Okay, let me see some. Okay, welcome. You're welcome. Right. Now, so where are all these being found? So let's go back to our lecture notes. So this is the invertible matrix theorem, and let's try to recap. Here, the matrix is invertible. First, remember that any invertible matrix must be a square matrix. Otherwise, you can forget about this. When he says that the matrix is invertible, then AX equals to 0 has the trivial solution. So he's saying that it must be the matrix A here, and it must be multiplying with all zeros such that it's the zero factor. Now, how do you see that? When you see it this way, it's difficult to appreciate. So let's write A as the column vector. A1, and let's play with only a 3 by 3, okay? So let's a concrete case, and therefore I will only have a 3 element of zeros. And then what am I seeing here? If this is the A matrix and this is the X, now I'm going to draw in different color first. Let's have the first 0 in red, the second 0 in blue. You'll realize that I'm going to multiply the red with the first column. I'm going to multiply the blue with the second column. Why do I say that? Let's see. Because it is, when we open up a matrix multiplied by a vector, it is a horizontal guy multiplied by x. So then you think that, oh, I have 3 elements of A1, A2, A3. But when you are actually seeing it, you realize that it is doing this. A1 multiplied by 0. This whole vector multiplied by a scalar 0 plus the second guy, A2, the whole vector multiplied by a 0. And then, of course, the green guy, A3 multiplied by the last guy 0. The trivial solution he's talking about is this guy. The 3 elements must be 0. So it's this guy, this guy, this guy in this order. The red, the blue, and the green. X must be this. Okay, so the invertible matrix theorem is basically teaching you a lot of things, and every question will only use 1 or 2 of them. Okay. All right, let's go back. So when he tells you AX equals to 0 only has the trivial solution, he's basically implying A inverse exists. That's what he's saying. Or he says A is invertible. Okay. Now, then he says, all right, go ahead and prove to us that this guy is also only the trivial solution. So he's basically saying AK X equals to 0. When this happens, the right hand side is 0. This is fixed. Huh? I give you right hand side. I never tell you what AK is. It's just A times A times A many times. K times. But I tell you that show us that this guy must be the trivial solution, which means he must be also the 0 factor. What's the information he told us? He only told us that. So the information he gave us was AX is equals to 0. This guy is the trivial solution. But he didn't tell you A times A times A up to K times. The trivial solution still exists. So how do we start? So we are going to start it this way. We say that suppose AK times X equals to 0 for X not equals to 0. That's not what he wants. He wants show us that X must be 0. But we start from the opposite way. Okay, we are saying that no, we can find X that is not equals to 0, but yet AK times a not 0 X can still be 0. So, and of course, if we show that this is false, then we get what we want. Okay, how do we show that this is false? How to show? Above is false. That this will never happen. Well, we know that A minus 1 exists. So let's write AK first. AK, this is AK, K times X. And now let's multiply on the left by A minus 1. If I multiply on the left by A minus 1, I multiply this guy by my, then I get a second guy. I get a second guy. I get a third guy. And you get the idea. And then I close this. And I close this. Now A minus 1 exists. Right? But hey, it doesn't matter what you get on the left, on the right, sorry, because let's call it C. C multiplied by 0 is equals to 0 on the right hand side. What about this guy? Then he says, hey, he's K times. This guy is K times. Let's strike this guy off. A minus 1, because I can open up the bracket. That's the idea. I open up the bracket and we can strike off. Then we strike off this guy. And then we keep on striking. And then all we are left with I. So what do we have? Ix equals to 0. I is the identity of size n. And identity times the x equals to 0 means x must be 0. So for this equation to be true, x must be 0. And then we have proven this. And what does x must be 0 mean in this equation? It means that AK is invertible. Okay? So in fact, he can actually tell you the question in a much simpler terms. Right? If he doesn't want to trick you, he could have told you if A minus 1 exists, then is A times A times A minus 1 exists. So if you use determinant, remember that the determinant of a product of a matrix, for example, if A, B, the determinant is equals to determinant of A times the determinant of B. What about the determinant of A times A? Is determinant of A times determinant of A. So if determinant of A is not equals to 0, then no matter how many times you have done this, then you are doing it this way. And therefore, if this guy is not equals to 0, no matter how many times you multiply, it will not be 0. And therefore, if you know determinant and you can use determinant to prove, it is a much easier affair. Okay? So, but if you do not know determinant, then just now how we show was one approach. Now, then you say, which approach should I use? So the idea is always come back here and then you'll realize that you have all these available same statement. He says that if this guy is true, all this is true. If this guy is false, all this is false. You can use any of the what do you call that statements to prove your question. Okay. All right. So I am at question 4 now. And I think that we would have time to finish question 5 and then we are done. Okay. 4B. Okay, 4B. Let me see 4B first. All right, let's explain this question again. AX equals to B is a consistent system. It means that, remember when he says consistent, it means that the equation AX equals to B is going to be true. The left-hand side, A multiplied by X, will produce a vector. Let's call this vector Y first, and this vector Y will be equals to right-hand side. When is the system inconsistent? Remember that I always give you an example. 1, 2, xy, just for example, equals to 3. And then, of course, to cheat, I say, hey, I'm going to give you another equation, 1, 2, which is exactly the first equation. But now, this guy's 4. Then, of course, these equations are not consistent because the first equation you give me is this. And the second equation, the left-hand side is 1, 2, which is the same as above, but the right-hand side is not the same. Then the system of equation is not consistent. It means that the lines in this graph will never intersect. All right, but when the system of equation is consistent, then what does it mean? It means that this x will multiply with a on the left, will give you the b. That's what consistent means. Okay. Now, here he's not telling you about invertibility and all. So he's only saying that, okay, I have x1. There is one solution. So he's going to say ax1 equals to b. So he explicitly tell you x1 is a solution. Then he tell you x0 is a solution, but not of b. Is the solution to the homogeneous equation. So he's saying ax0 equals to 0. So let's have, so always in my mind, I need to figure out when is this true. And after a while, you realize that I only give you a single example. And then the single example is 2 minus 1 equals to 0, 0. Then if you're not happy with this, then I can actually give you another number, 1. And then this guy will be, I guess, minus half. And if you're not happy with this guy, you can get another number. For example, minus 1. And I guess this guy will be plus half. Then all this, you realize that will be equals to the 0 vector. So in fact, so this is another example. You see the equations with a lot of, or in fact, infinite number of solution for this guy. Okay. All right. So now we know that there are many x's that will satisfy this one. And we call him x naught. Now let's plus together. So we have ax1 plus ax naught. And the right hand side is interesting. It's b plus 0. So the right hand side doesn't change a thing. Yeah. So this very strange creature, the homogeneous solution, doesn't change a thing of the what do you call that? The output. So by using any solutions here, doesn't change a thing. So is it a good thing? Depends. It means that you are allowed to have. Okay, I'm going to show you this. So what do we do? We're going to combine this guy. Because we just distribute, right? Or we share the A. So the trick is this: we can introduce any X naught, and the output doesn't change. And so this is the degree of freedom we are talking about. You can modify your control. Imagine your X are knobs which you can play with, and that and yet the output don't change. So maybe one of your X is, let's reduce the amount of electricity, and hopefully the equation don't change. Wow, that's good. Yeah, maybe another knob you say, let us decrease everybody's salary, and yet the output doesn't change. So that's the X knob. Maybe X1 will be, let us increase the flow of water. Okay, then B will change, for example. So that's the idea. Some parameters of X doesn't change. But please don't confuse X0 and X1, because we are going to write AX. So we write AX. So this is X equals to B. What is X? X is a vector. So X is a vector of what size? So it depends on A, of course. Let us maybe, so please don't confuse X1 and X0. So this X1, this X vector is a vector of X1 plus a vector of X0. So maybe if we have element A, B, C, then let's say we call it D, E, F, then we can just add them up together. That's the idea. So these guys are vectors themselves. Okay, so maybe if you look carefully, the x's are in bold to tell us that it is a vector. Okay, so this x is this guy is this guy, and this guy is this guy. All right. Okay, so what now? Number 5. Maybe I have another 5 minutes, and then I'm done. Or do you guys want to do it next time? Okay. Okay, then let's continue. So he says, I have a square matrix A, and I have linearly independent columns. Imply A is square, because he told us n by n is invertible, because he tells us column are linearly independent. Where do I know this? Number 5. The columns of A forms a linearly independent set. All the columns A1, A2 up to AN are independent. What does independent column means? So let's have A1, A2, AN. Independent means, let's call this X1, X2, Xn. So now please don't be confused. Here the X1 is a scalar. X2 is the scalar in this whole vector of X. Now, if we want to be very clear, sometimes I underline to say that this X is a boldface, which to underline below to say that it's a vector. When it is an element of a vector, then it's a scalar. Now, when we see this, we understand that all we are doing is a matrix vector multiplication is nothing but x1 multiplied by the whole vector a1 plus x2 multiplied by the whole vector a2 and xn multiplied by the whole vector an. And then to check whether they are linearly independent or not, then we wanted a vector of 0. And then if x, all this, the scalar associated with the multiplication, if the results is 0 and all these must be 0, then they are linearly independent. So that's the definition of linearly independent. All right, once we have columns of A that are linearly independent, what do we do? Well, then we have just found out that A is invertible. Show that A2 columns are also spanning R2. Then if you look at it very carefully, the columns of A span Rn because n is a n by n matrix. So he used a different terminology to ask you, is A2 invertible? So it is a very roundabout way, okay? It's a very roundabout way, but he's basically asking you to understand all the terminologies associated with invertible matrix. If you want to be direct, he says A square and invertible is A2 invertible, finish, right? But he uses show that the columns of A2 span R2. All right. But of course, if we have to prove, then it's a different story. Okay, so now how do I do it? But yet, you know, if we understand, if we already know product of invertible matrix is invertible, then we will prove. So this is one way. What about the other way? Well, we let C equals to A squared equals to A by A. Note, A minus 1 exists. We are going to pre-multiply the equation with A minus 1. So we have A minus 1C equals to A minus 1 multiplied by A times A. We have just reduced to I times A. So we are still not happy with this. A minus 1C. We again pre-multiply with A minus 1. So implying A minus 1C equals to A minus 1, A equals to I. So we have arrived implying, what is C again? So C is A squared. So A minus 1, A minus 1, A times A equals to I. So this guy is the inverse of A. Since the inverse exists, therefore A times A is invertible. And since it is invertible, and A times A, the size is n by n, n by n, n by n. Therefore, the column spans R2. Okay, so read the question carefully again. Actually, he never tell you that it was R2 until the end. So actually, n by n is a 2 by 2 matrix. All right, so these are some of the tricks he's playing. Is it a typo? Should be Rn? Yeah, it might be Rn, but here he's telling you that it is R2, and therefore n by n is a 2 by 2 matrix. That's what I believe anyway. Okay. All right. Yep, he says n equals to 2, correct. Now, 5a. Okay, I have one more question to go. And then we are done. Show that if AB is invertible, so is A. So the theorem 9. So let's go and look at the invertible matrix again. There is a matrix D. So this is right multiplied by the matrix A. So A is an invertible matrix. When A multiply on the right hand side by another matrix and give you I, then A is an invertible matrix. Interestingly, he says that C, if you left multiply, is also okay. In fact, you realize that C and D are the same matrix. All right, but never mind, let's proceed. If A is a 1 by 1, then it can only span, yes, correct. Yes. If A is invertible, then the number of rows gives you the dimension of the span. Yes, correct. Okay, because you look at this theorem. Yeah. So that's why all these are going on and he needs, so I'm going to erase this first, all this, and I'll show you where the little n is. So the little n is running around. First, he must tell you that it's a square and it has a number of rows and columns to be little n. And then he says that, all right, he's going to span Rn. So that's the first one. B is n because this is a n by n and this guy is n by 1. So B must be n by 1. So there's n coming out again. Where else n comes out? Here. A is row equivalent to In. What does it mean? It basically means that if you have a matrix A and you start to row reduce it, remember by row reducing it means that we form a pivot and we form some values and then we have zeros here and you get some, and then you keep on doing this. And when you finish doing this using the Gauss, not the Gaussian elimination, but the Gaussian Jordan elimination, because the Gaussian Jordan is, what do you call that? The Gaussian Jordan basically will reduce not only to an upper triangle or the pivots, but will reduce to the identity. So if you play with the Gauss Jordan, you will realize that he will reduce it to identity. Will we go through the lab codes for lab 1? No. Yeah. Okay. So A is row equivalent. So okay, so let's come back to our tutorial. So we use theorem 9. So all we are interested is we want to find A, D equals to I. But here is, okay. So AB is invertible. What does it mean? Well, let C equals to AB minus 1. Yeah. Because he already tells you AB is invertible. Now, what about ABC? Isn't it just bring this down? And of course, AB multiplied by his inverse is I. So far, okay? And now we open up the brackets. We don't change a thing. It's still I. And now we close the bracket because we want to check A. And now we say that this guy be D. Still I. So you look at theorem 9. Theorem 9 says AD equals to I. There exists a matrix D such that AD will be equals to I because A is invertible. Okay, so then proof. You okay with this? Okay. So I think we are done. So this is the easiest way to prove this. And then I will upload this. So we have question 1 to 5 in this video for over an hour. Right, with that, I think next week we'll go through the rest of the questions if we have time. If not, you will see the videos of other tutorial groups which will do the other questions so that we will catch up. All right. With that, thank you very much. Have a good weekend. Bye. Chat. Oh, thank you. Thank you. Yeah. Thanks, everybody. Okay. Stop sharing. Thank you. Thank you. Yes. Thank you too. Okay, we end.